Hello everybody, long time no see. Anyway, welcome back to another discussion on dynamics. Today we will start a new topic, namely, we will start work energy of rigid bodies. If you would like to place this topic on our timeline, it's here. As you can see, we are almost there. So plan for today is following. We are just going to do brief lecture review and then 2 examples. So as usually, without further ado, let's dive straight into our discussion. Let's start with a brief lecture review. I prepared something before recording this video. Okay, brief lecture review. So, since we are in work energy method, we are just going to use our well-known work energy equation. So, T1 plus V1 plus U12 non-conservative equals to T2 plus V2. So what's the main difference between work energy method for particles and for rigid bodies? The biggest difference is in the way we calculate kinetic energy for rigid body. Excuse me. Before I start talking about these 2 equations, please have a look at the drawing on the left. Oh, excuse me for that. What do we have in here? We have a rigid body. We obviously know its mass and moment of inertia about its center of mass, plus its moment of, if its center of mass, its location, it's known. Moreover, we know velocity of this point C, and we also know the omega of the body. Great. So with all of this information known, we can write down kinetic energy of our rigid body. It will be half m vc squared plus half ic omega squared. First part is called linear kinetic energy, and the second part of this expression is called rotational kinetic energy. In United States, this expression is called kinetic energy for rigid bodies. However, there are some countries that this expression is called Koenig's theorem. I might be using this expression interchangeably. All right, so this is the most general case to write kinetic energy of rigid body, and you can always write it. However, if you locate let's say, a pin in the system, that our body is pinned at some point, then think of going for this expression. Kinetic energy is equal to 1/2 Ia omega squared, where A is of course pin. And Ia can be obviously calculated from parallel axis theorem or Steiner's theorem, right? Yeah. So these are 2 ways to calculate our kinetic energy. Another thing another slight change to our kinetic work energy equation is how to calculate potential energy. Still the expression is mgh, however this time h is elevation of center of mass. As you can see in the picture on the left, I placed our datum here, and our C is h above the datum. That's why potential energy of our body is mgh. Okay, I think I have nothing else to add when it comes to brief lecture review. So without further ado, let's maybe start doing our example number 1. Let's do it. As usually, please read and understand the problem statement. but since this is a pre-recorded content, feel free to pause the video and familiarize yourself with the problem statement. Okay, so what do we know in here? First of all, we have two cylinders, yes? We have one that is hollow and one that is thin-walled. Sorry, what I'm talking about. One that is solid and the one that is hollow, yes? So the question is, which one will be faster? Okay, so what do we know? These are our knowns. We know their masses, we know their geometries, we know that there is no slip, we know that they start from rest, we know the incline also, excuse me, and I think we also know their moment of inertia, right? Because IA, if I remember correctly, is 1/2 mr squared, and if you look at the equation page, you will find that moment of inertia of a ring, so IB, will be mr squared, if I remember correctly. Okay, and they ask us to find velocity of each of them at distance b. I will define the distance b in a second. Okay, so let's solve our problem. Let me draw two drawings. One at configuration 1 and the other one at configuration 2. Okay. All right, so this is my incline. And, you know, it's too steep. I will redraw it. Let's say such incline. I'm gonna copy it. Okay, let's say that our cylinders start from here. Okay, we're gonna solve the same problem for these two cylinders simultaneously. Okay, this is our center of mass of these two cylinders. And this will be our datum. Okay, my datum. So you guys can probably clearly see that this will be distance b. Okay, this will be distance b. Okay, and we have no slip. It starts from rest. And that's all. I think all of the givens are already on the board. Okay, let's write down our equation. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And exactly as in the past, we'll just find these five guys. T1, V1, T2, V2, U12 non-conservative. Okay, system starts from rest, so I can put 0 in here. I think that at the end, we have some velocities, yes? So I think that in the end, we have velocity c, right? And also we have some omega. So we can write following Koenig's theorem: 1/2 m v vc squared plus 1/2 ic omega squared. Since there is no slip at this point, we can relate vc and omega. We can just write here that omega is equal to vc divided by r. And let's plug this equation in here. I will just move it somewhere else. And we can write here 1/2 m plus ic r squared vc squared. Okay, now potential energies v1 and v2. So I think that I located our datum here. So potential energy at the end will be 0. So this is 0. And at the beginning, potential energy is following distance. It's this distance, right? H, which is equal, if this is theta, this should be equal b sine theta. So in here I can write mg times h or mg b sine theta. Okay, great. So we have 80% of the problem done. Now, one last part. Work of non-conservative forces. Before we find work of non-conservative forces, we must draw what non-conservative forces act on our system. Okay? So, let us draw FBD, but only non-conservative forces. Only non-conservative. So I will skip gravity. Okay, so this is our cylinder. These are our cylinders. Okay, I think that there is this non-conservative force acting on our system, normal force, and also there is friction force, yeah, acting on our body. And I don't think that there are any other non-conservative forces acting on our system. Okay, so in here we have to deal with work of two forces, u-12 of Tf plus u-12 of n. Okay, so let us do these integrals. Integral from some point A to B, Tf times ds, let's say dsq, because I would like to call this point Q. That point of contact between cylinders and incline is Q, okay? And similar integral from some point A to some point B, actually exactly the same points A and B, of n times dsq. I just would like to remind you guys that there is no slip at point Q. Okay, and that's why I think I would like to ask you to pause the video right now and try to think what is the values of these integrals and why. Okay, so I just would like to bring your attention that there is no sleep at point Q. Okay, so the question is, what is dsq because of that? And once you have dsq, can you please tell me what are the answers for these two integrals? In other words, what are the works of these two forces? Feel free to pause the video right now and try to answer all of these questions. Take as much time as you want. All right. So for those of you who got it right, congratulations. And for those of you who just came here to put their notes together, the answer is obviously dsq is zero vector, because there is no sleep at point Q. So our forces N and TF, they do work on zero distance. That's why they actually do zero work. This is zero and this is zero. Because of this, because dsq is zero. Great. So our u12 non-conservative is zero. Great. We found five of these guys. What was the next step in our solution? Do you remember? The next step was plugging back everything into our original equation. Excuse me. Plug everything back. Okay, so what did we have in there? I believe that we had there mg as mgb sine theta, right? And that was equal to this expression. This is equal to 1/2 m plus ic r squared vc squared. Okay. So we can just write that our vc is equal to square root of 2 mg b sine theta divided by m plus ic r squared. Right? I believe so. Okay, so we found, we solved the problem in general, yes? We solved the problem for any cylinder rolling down the incline. However, we know that for the solid cylinder, solid cyl, we have ic equal to 1/2 m r squared. So let's plug that into here. Okay, so we actually will have, so IC, I think IC is equal to IA, right? Because IC will be equal to IA. And this is equal to 1/2 mr squared. So we have, in here we have VC solid will be equal to square root of 2mgb sine theta 3 divided by 2 m, right? I believe so. Yes, so this will be equal to 4 divided by 3 times GB sine theta. Okay, let's leave it like that. Now for the thin wall, we know that IC is equal to IB. This is equal to MR squared. Excuse me. So that would be IC hollow. Oh, sorry. Of course, VC whole will be equal to 2mgb sine theta divided by, I believe, just 2m. Okay, so this is equal to just gb sine theta squared. Okay, we found out our solution. This is our VC of solid cylinder, and this is our VC of hollow cylinder. Which one is larger? Naturally, it's VC solid. We can even provide the ratio of them. So our VC solid divided by VC hollow is equal to 4 divided by 3 squared. Okay, this is our answer. And this is the end of problem 1. This is the end of example 1. I hope I explained it clearly. If you have questions, please feel free to post questions on Piazza or visit us during our office hours, or ask us questions during discussion sections if we have time. All right, so now what? Let's do example number 2. Let's do it. As usually, feel free to pause the video right now and try to read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have two gears, big one, A, and small one, B. The radius of the big one is 0.25 meters, and the radius of the small one is 0.1 meter. We also have a moment or a torque applied to the small gear. What do we know about them? We know that nonce gear A, we have mass A that is equal to 10 kilograms, and we also know that Ka is equal to 0.2 meters, while radius of A is equal to 0.25 meters. When it comes to gear B, we know that its mass is how much? 3 kilograms. Its radius of gyration is 0.08 meters, and radius of gear B is 0.1 meter. Oh, we know that system is at rest. system starts from rest. There is no friction between these gears. And we know that our M is 6 newtonometers. And what do they ask us to find? Aha, they ask us to find in part A and in part B. So they ask us to find theta B such that omega B is 600 RPMs. I believe that this will be 600 2 pi divided by 60. So this will be 20 pi radians per second. Okay, so we must find theta B when omega B of this value is reached. And also we should find tangential force between gear B that gear B exerts on gear A. So it will be T measured at B measured at A generated by B. So they ask us to find that. Okay, I think we know everything. Let's start our solution. So as usual, I'm just gonna draw two drawings at two configurations. Configuration 1 and configuration 2. So this is my first gear. This is it's okay. It's support. Then this is our second gear, small one. Okay. We have that torque applied here. I think that's all. Okay, we can write in here that system starts from rest. System starts from rest. I don't know why I wrote it again. Yeah, I just wrote it like 3 minutes ago. Yeah, sorry for that. Okay. And let's see what happens at configuration 2. So at configuration 2, we have the same gears, but this time they rotate, right? This guy will have omega B, right? And this guy will have omega A. And I think that's all. Yes, nothing more interesting is happening in here. Okay, so now let's write our equation. T1 plus V1 plus u-12 non-conservative is equal to T2 plus V2, but with one caveat, okay? This is equation for the entire system. For the entire system. Okay, so I'm not looking at each body separately. I am just going to look at the entire system altogether, okay? So all the internal forces I don't care about, okay? So in particular, this force I don't care about. This is force between these two gears, okay? I don't care about it. So right now let's find these five guys. T1, V1, T2, V2, u-12 non-conservative. Okay, so what is T1? Ah, that's trivial, it's 0. System starts from rest. Okay, what's T2? Aha, so our center of masses are in here, right? As you can see, guys, these green points, they don't move at all. So actually our kinetic energy equation simplifies tremendously. We can just write two expressions for rotational kinetic energy. 1/2 IA omega A squared plus 1/2 IB omega B squared. Yeah, as you can see, kinetic energy is so-called additive function. That means that kinetic energy of the entire system can be expressed as a sum of kinetic energies of each of the components of the system. This is exactly what I did in here. I have kinetic energy of the first body plus kinetic energy of the second body. Okay, how about potential energy? I think we don't have any springs in the system. No, I don't see any. I also think that our bodies do not change elevations, right? So I can put 0 in here and 0 in here. No springs. Bodies don't change elevation. Elevations. I think I can do a better job here. Okay, how about work of non-conservative forces? Yeah, because again, we have 80% of the problem done. Are there any non-conservative forces act on our system? Yes, there is a couple of them. Yeah, on the entire system. So I think that if I copy this, for example, you guys can clearly see that we for sure have u-12 of M acting here, but there are more non-conservative forces acting in our system, right? But their work will be 0 because we have these forces, yes, AY, AX, and BY, and BX. Yeah, these reaction forces at these pins. However, what is the displacement of these pins? What are the displacements of these points? Yes, displacements are 0 vectors, right? So that's why work of force A and work of force B will be 0. So we can just ignore them. Or let's ignore them. Maybe we shouldn't ignore them. But just to speed the things up, we are going to ignore them. Okay, so we ended up with only one non-conservative force that actually does some work. Okay, so let's do our integral. So we integral from some point A to B of M times d theta B. Yes, because this is our gear B, d theta B. So d theta B is infinitesimal rotation increment of gear B. And I think that they are aligned. Yes, so we can actually put our integration bounds here from 0 to some theta B, and this will be basically from 0 to theta B M d theta B. Oh, sorry, no vector this time. So this will be, and this is constant. So the answer is just M theta B. Okay, we found our work of non-conservative forces. So let's plug everything back into our original equation. So we will have here M theta B. This is equal to 1/2 IA omega A squared plus 1/2 IB omega B squared. Excuse me again for that. So I think that now we should find some relation between omega A and omega B. That's trivial, right? This will be just a gear ratio, yes? Gear ratio. We can always write RA omega A is equal to RB omega B. And I think that they ask us to find, we know what omega B is, yes? So let's express omega A in terms of omega B. RB divided by RA omega B. And let's plug this one here. So we will end up with m theta B is equal to 1/2 MA Ka squared RB squared RA squared plus MB KB squared divided by omega B squared. Okay, so our theta B can be found using such expression. 1/m, plug in values. Theta B is equal to, if I remember correctly, 1/6 1/2 times 10 times 0.2 squared 0.1 squared 0.25 squared plus 3 0.08 squared times 20 pi. Okay, grab your calculators and obtain that our theta B is approximately 27.371 radians. However, I think that they ask us to find revolutions, right? Let me scroll up the board. Yes, find number of revolutions. So let's do that slight adjustment to our answer. So this will be, theta B will be approximately 27.371 divided by 2 pi. And if you grab your calculators again, you will obtain that this is approximately 4.356. Interesting. 6 revs. Okay, so this is our answer part A. Answer part A. Okay, I hope I explained it well, but it's not a big philosophy, right? If you allow me to scroll up the board, we just follow our recipe from the previous part of the semester, right? We just write down this expression, and then we just find these 5 guys using our new techniques for finding kinetic energy and potential energy. As you can see, finding work of non-conservative forces is exactly the same as previously, as it was like a couple of weeks ago. Then we just plug everything back in, and we solve the problem. Okay, so I think that we should still solve part 2, right? Where they ask us to find T at A generated by B, right? So it will be that force in between our gears. Before we start solving for TAB, I would like to note that TAB, so the force acting on gear A and generated by gear B, is exactly the same as TBA. So force acting on gear B generated by force A. Of course, magnitude-wise. amplitude wise. Which Newton law is that? Feel free to pause the video and think which Newton principle is that. First, second, or third. Okay, so for those of you who got it right, congratulations. And for those of you who just came here to put their notes together, this is according to third Newton's principle. Okay, so now I would like to use the work energy approach, okay, but only run on gear B, okay. So I'm going to write one more time config 1, config 2, but only gear B, so that little one. Okay. We have M acting here, and we will also have our TBA acting this way. And our thingy starts from rest. And in here it has some omega B. We just found, by the way. This config A and config B, sorry, config 1 and config 2 are exactly the same configurations as in part A. So T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. T1, V1, T2, V2, U12 non-conservative. Okay, let's find these 5 guys. System starts from rest. This is 0. There are no springs in the system, plus our gear B does not change its elevation. At the end, our gear B has that much kinetic energy, 1/2 IB omega B squared. And there are only 2 forces acting in our system, as you can see in here. Of course, again, there is a force at pin B, but it does not do any work. So there are only two forces that do any work. So it will be again U12 of M plus U12 of TBA. Okay, let's solve these integrals. So this will be integral from 0 to theta B of M d theta B plus integral from 0 to theta B of TBA RB d theta B. Oh no, can I squeeze that subscript here? Let me see, I must probably shift everything a little bit to the left. Oh no. Okay, let's see if I can do that. I think I can. Okay, and I think I forgot about minus somewhere. Minus will be here. Minus will be here. Yes, because I assume that our d theta B rotates this way in a positive direction. Okay, So our TBA rotates in the opposite direction. Okay, so they are both constant. So let's say that this will be equal to m theta b minus TBA RB theta b. Okay, so we found our 5 guys. We can plug everything back into our original equation. Okay, so we will end up with m theta b minus TBA RB theta b, and this is equal to 1/2 mb kb squared omega b squared. Okay, so our TBA is equal to just m divided by RB minus 1 divided by RB theta b 1/2 mb kb squared omega b squared. I hope I didn't do any mistake. It looks fine. So let me plug in values. So TBA is equal to 6 divided by, if I remember correctly, this was 0.1 minus 0.1 times 27.371 times 1/2 times 3 times 0.08 squared times 20 pi squared. Okay, grab your calculators and find that TBA is equal to approximately 46.153 newtons. And this is our answer to part B, because our TAB will be equal to exactly the same value, but it will be pointing opposite way according to the third Newton's principle. Okay, so that's all I prepared for today. I hope everything was clear, and the main take-home message from this discussion is basically training this recipe. So just remember that in order to solve problems using work energy method, just first write down this expression, then these five guys correctly, of course, then plug them back in to our original equation, and the rest is algebra. So I hope that was helpful. Thank you for your attention, and see you next time. Bye.